Well, hello everyone. We're going to keep going with our chapter on forced and damped simple harmonic motion. If you remember last week, we arrived at the following ordinary differential equation: x double dot plus px dot omega squared x equals 0, where the second term involves b, a constant, a damping constant, which is positive. So if it wasn't for that second term, this would be the simple harmonic motion, and now there's a damping term added. And to solve it, we tried a solution of the form x equals exponential rt, where r was the constant to be determined. So if you substitute this into the ODE, you will find a quadratic in the end. That's simply because the first derivative, the x dot, is going to be r times exponential. The second derivative, x double is going to be r squared times exponential. And then if you substitute, you can divide across by ERT, and you end up with this quadratic, r squared plus PR omega squared equals 0. So that's the way to solve it. You know that now r, which you had kept unknown, is in fact a root of this quadratic. So you may compute the roots using the general formula for roots of a quadratic, which is as follows: minus b plus or minus square root of b squared minus 4a, a is 1 here, c, which is omega squared, divided by 2a, so it's just 1/2 in front. So as we said earlier, it all depends, the nature of the roots will all depend on the sign of b squared minus 4a minus 4 omega squared. So we're going to treat the cases in turn. The first case is when b squared minus 4 omega squared is negative. So in that case, the square root of b squared is the square root of a negative term, right? It's going to be minus square root of minus 4 omega squared minus b squared. Now that bracketed term is positive, and so you can see it's going to be plus or minus I square root of omega squared minus b squared. At the moment, it's all very general. Don't worry, we'll do an example really soon with numbers, and you will see how it reads. So now I have my solution as follows. Let's just say I'm going to write my root in a more compact way. I'm going to let kappa be 1/2 square root of 4 omega squared minus b squared. Then I can write the roots as follows: minus p over 2 plus or minus I kappa. Right, that's the same as above. And now my solutions to the ODE are exponential RT, which I may rewrite as exponential minus B over 2 plus or minus A kappa T, and then exponential A plus B is exponential A times exponential B, so I can expand it as follows. But here I have an exponential of a real term, so I keep that. Times exponential of a purely imaginary term. And I can use Euler's formula. I know from the previous lecture that this is cos plus or minus kappa t. Cosine is an even function, so it doesn't matter what the sign is in front. Inside the argument, and then plus sine of plus or minus kappa t. Sine is an odd function, so if it's a minus, I have minus in front, plus I'm going to have plus in front. So I'm going to write it like this. That's correct. And in fact, I have two solutions, right? The one with the plus sign, the one with the minus sign. And so if I have two solutions, I know that I have the general solution. I just need to write it as a linear combination of each solution if you want a double infinity of solutions. So I'm going to have A, an arbitrary constant, times the first solution, the one with the plus sign, and then B, another arbitrary constant, times the second solution, the one with the minus sign. And now, oh, I forgot the T here. I see common terms, right? I can regroup the terms that are in cos. I'm gonna have A, or actually I can regroup that too. I have A plus B exponential minus B over 2t times cos. And then I can regroup the terms in sine. I can put the I in front. Now it's going to be A minus B exponential minus t sine kt. And then A and B are arbitrary constants. So A plus B is an arbitrary constant. I times A minus B is an arbitrary constant. I'm going to call them C and D. Or where C is another arbitrary constant. And D is another arbitrary constant. And I'm going to frame this. Sorry, KT to reduce size. Here. Oh. Okay, for some arbitrary constants C and D. And that's the general solution when the roots are complex. So that seems hard to memorize. I mean, do I really have to memorize that formula? Do I have also to memorize that kappa is square root of 4? No, you don't have to memorize any of this. When the roots are complex, you just know that, say, when roots are of the form alpha plus or minus I beta, the solution is C exponential alpha t cos beta t plus t exponential alpha t sine beta t. That's all you have to memorize. And at the end of the lecture, I'll write this into a table. Okay, and just like when there was no exponential, there was just cos and sine when we were doing simple harmonic motion, we can, just like in that lecture, we can rearrange the cos and the sine into a sine ax plus b or at plus b here. All right, so I won't go into the calculation because there's not much to learn from it, but you'll know from the previous lectures on simple harmonic motion, like be arranged like this: exponential minus p over t over 2t and then sine kappa t plus alpha, where alpha is just constant. And the only reason why you want to do that is just to get a sense of how this function behaves with time. It has two parts. The first one is the amplitude, but the amplitude is not constant. It has an exponential term here, exponential decay. Remember that b is positive, so minus p over 2 is negative. And then it also has an oscillatory term here, just sinusoidal variations, which are damped by the amplitude. So typically, it will look like this. There will be the exponential decay of the amplitude, and it will create an envelope for the variations of the function, which will be oscillating up and down, but with a decaying amplitude. So the amplitude decay is the envelope, and then the oscillatory terms, let's spell it right. Oscillatory term. And that's typical of a damped solution to the equation above. Okay, so this was all very general. We're just going to do an example now, and let's see how it goes. So in this case, b is a half and omega is a half. So remember that the equation of motion is x double dot plus bx plus omega squared, bx dot plus omega squared x equals 0. which here reads as follows: x double dot plus a half of x dot plus a quarter of x. Omega squared is a quarter if omega is a half. So when you see that type of equation, second order linear differential equation with constant coefficients, you know that the solution is going to be of this form. You don't know which case you're in. Is it positive? Is it real roots, complex root, repeated root? You just try it. Try your hand at it. So usually you start like this, then you compute x dot, x double dot, and you substitute to find. So x double is going to be r squared ERT plus a half of ERT plus a quarter ERT equals 0. And I see that there's ERT everywhere, so I divide across by ERT. I end up with r squared, so half of r plus quarter. I was expecting a quadratic, so now I can solve it. I look for the roots. R equals minus b. B is a half here. Plus or minus square root of b squared. It can be a quarter. Minus 4 times a, which is 1, times c, which is a quarter, divided by 2b, 2a, sorry, and a is 1 here. So I end up with a half of minus a half plus or minus square root of a quarter minus 4 times a quarter, that's 1. So I keep going, a half minus a half plus or minus square root of, or minus 1, that's minus 3/4. So I have square root of a negative term, so I'm going to have complex roots here. A half minus a half plus or minus I square root of 3/4. And then a half times minus a half, that's minus a quarter. Square root of 3/4, that's square root of 3 over 2 times a half, that's going to be square root of 3 over 4. Plus or minus I square root of 3 over 4. And so I have complex roots. The real part is minus quarter. The imaginary part is plus or minus square root of 3 over 4. So I know that the solution is simply going to be x of t is an arbitrary constant times exponential, and here I put the real part, minus a quarter t, then cos of the imaginary part, square root of 3 over 4t, plus b, again, exponential minus quarter, times sine. That's my solution. All right, that's all I need to remember. I start from my ODE I look for a solution in an exponential form, I substitute, I end up with a quadratic. If the quadratic gives me complex roots, I know that the real part is going to be going into the exponential, and the imaginary part is going to be going into the cos and the sines. Just to show you on the next slide what it looks like, I've taken C is 1 and D is 0. Oh, I'd call them A and B. Okay, these are imaginary, these are arbitrary constants, so I can call them A, B, or C and D, it doesn't matter. But if I take the first one to be 1 and the second one to be 0, I'm going to end up with this function here. And if I plug that into any computer system, say Wolfram Alpha for instance, I will get this curve here, the thick curve that's oscillating and decaying between the exponential shapes that are in dotted lines. Okay, bounded above and bounded below by the exponentials. Okay, so that was the first case when the what's called the discriminant of the quadratic is negative. Next case, what happens when the discriminant of, writing here, when b squared minus 4 omega squared is positive? Then you know that the quadratic equation has two real roots. Alright, there's going to be, we'll call it R1, will be the one with the minus sign, and it's going to be R2, say the one with the plus sign. So if you have two roots, then you have two solutions. Solutions are exponential R1t and exponential R2t. And that's nice. If you have two distinct solutions, then you have the general solution. It's going to be x of t equals c, an arbitrary constant times the first solution, plus d, another arbitrary constant times the second solution. Very simple case, at least easy to memorize. And then when you look at the solution, you see that there's going to be no oscillation here. No. Because there is no cos or sine terms. And another thing you notice is that, so recall, okay, we want to here not that p squared minus 4 omega squared is less than b squared. Yeah? P squared is a positive number. If I subtract minus omega squared, 4 omega squared, which is I'm gonna end up with something less than the b squared. Yeah. So that tells me the square root of b squared minus 4 omega squared is less than b. Yeah, square root of b squared is a positive number, b is a positive number. So that's all good. And now if I bring this to the right hand side, I can see that this quantity is negative, and that's root R2. Yeah. Also, P is positive, so minus P is negative. Minus square root P squared minus 4 omega squared is also a negative number. So that tells me that minus P, a negative number, minus P squared minus another negative number, that must be negative. So both R1 and R2 are negative numbers. And so my solution above is just going to be decaying with time. It's not an exponential growth, it's an exponential decay. Decaying exponentially. That's what you call overdamping. The damping is so strong that there's no oscillations at all. So practically, let's look at this example here. Motion of a mass of 1 kilo attached to a spring with stiffness 1/4, K equals 1/4 with damping force minus 2 x dot. Alright, so I'll just write Newton's law. Ma equals F, so it's going to be mx double dot. So first there's the spring force minus kx, and then there is the damping force. In this case, you're told is minus 2 x dot. So if I enter m is 1 and k is 1/4, I end up with this ordinary differential equation: x double dot plus 2x dot quarter of x equals 0. Okay, I look at it, I see that it's a second order ordinary differential equation with constant coefficients. So I can try an exponential type of solution. If I substitute this inside, I know I will end up with the following quadratic: r squared plus 2r plus 1/4 equals 0. And now I know how to solve this. Roots of the quadratic are going to be r equals minus b, so here b is 2, plus or minus square root of b squared, that's 4, minus 4 times ac, divided by 2a, so I have a half, minus 2, plus or minus square root of 4 minus 4 times 1, so that's just 1. And so I can see that I have two real distinct roots. R1 is going to be minus 2, that's going to be minus 1, plus square root of 3 over 2, and R2 is minus 1 minus square root of 3 over 2. Two distinct roots, two real distinct roots. And you could check that minus 1, so I'm trying this on my calculator now, plus square root of 3 divided by 2 is indeed negative for R1, and then R2 is clearly negative. Two real negative, and so both solutions are going to be decaying. The general solution is x of t equals c exponential R1 t. It's going to be minus, I'll write it like this, plus d, so minus 1 and I'm in the case of overdamping. Oh, I had it there. If you were to enter this into a mathematics software, you will end up with this type of solution. No oscillation, just decay, rapid decay towards 0. Okay, so these were the most general cases. There's a very special case, and that's more like a mathematical oddity. It's when you have a double root, right? When you have b squared minus 4 omega squared equals 0. Write it like this. Then the square root is 0, and then you have just the one root. It's called the double root. R1 equals R2 equals minus p over 2. So you know from trying a solution of the form exponential RT that you can find one solution. If we want the general solution, we need two solutions, right? So try exponential ERT gives only one solution. How are we going to find a second solution? Well, we're going to try this here. T times ERT. Just for fun, let's see if that works. Right, I'm going to substitute this into x double dot px dot plus omega squared x equals 0. So x, I have it. I'm going to need x dot, so I just differentiate this. So now that's the product rule. First, so if u is t and v is ERT, I'm going to do u prime v, derivative of t is 1, and v is ERT, plus u v prime, derivative of ERT is going to be r ERT. Yeah, just rewrite like this. And then I compute the second derivative. Now I have to differentiate those two terms. The derivative of exponential is going to be r ERT plus r, and then again I have the product rule. I just did that. ERT r ERT, which is, so I have 2r ERT plus I have r times t times r, so it's going to be r squared t ERT. Okay, I have my three terms now. One here, one here, one here, and I can substitute into the differential equation. So let's go for it. X double dot, I just rewrite it here. Where is this going? It seems awfully complicated. Plus bx dot, so now I have to multiply the line above this by b. T plus omega squared ERT equals 0. I can see I have ERT all across, so I can divide by this just to tidy up a bit. So I'm going to have constant terms, 2r plus p, and then I'm going to have terms in t, r squared plus pr equals 0. Is that possible? Oh, wait. Oh yes, for omega squared, I know omega squared is, I'm going back up here, omega squared is p squared over 4. Yes, okay, so is this really equal to 0? Well, I must remember first that r is minus b over 2, so I just replace here. And I can see how the first two terms are going to cancel out here. And then here, in the t terms, I'm going to have minus b over 2 squared, so that's going to be b squared over 4 plus b times minus b over 2. And then omega squared, if I go back up, omega squared is b squared over 4. Over 4. Is this equal to 0? Yes. Yeah. That's 0. And then here, I can see I have the middle term is minus b squared over 2, and then I have b squared over 4 plus b squared over 4. That's also 0. So the conclusion is that x equals t exponential minus p of t is also solution. So that's the other thing we must remember. If we end up with a double root, trying ERT only gives you one solution, but then we know from now on, from this proof we just did, that multiplying that solution by t is also a solution. So I'm just summarizing it here. When R minus P over 2, that's the double root case, then one solution is exponential minus P over 2t, exponential RT. Another solution is t times that solution. That's what I've written here. If you have two solutions, then you have a double infinity of solution. That's a very special case, the so-called critical damping case. Again, no oscillations, and again, decay towards zero as t goes to infinity. So, just to summarize this lecture, you will be expected to know how to solve this equation here, which is a simple harmonic damped equation. First, you compute the roots of the associated quadratic equation, and then you just look at their nature. There could be two distinct real roots. In that case, the general solution is going to call the constant C1 and C2. You can call them AB or CD. And that's called overdamping. If you have repeated roots, then x of t is going to be C1 ER1t plus C2t R1t. And that's called critical damping. And finally, if you have complex roots, you look at the real part, then you put that into the exponential, and the imaginary part you put it into cos and sine. And that's called underdamping. That's it for today's lecture. Thanks.